So this is an introductory video about databases, and I'm going to talk in these videos about the relational model, and then we'll be looking at operations and some of the relational algebra which is applicable. Now, really this subject is all about how do we store data and how do we sort of store it and manipulate it in certain ways. How do we model data inside a computer system? And until the 1970s, there were lots of different ways of doing this, and the way that you would store data very much depended upon the combination of hardware and software that you actually had. And there were some typical models that were in use. It could have been a kind of tree structure, which would have actually looked more like something like this. You'd have had bits of data loosely connected to other bits of data in a kind of upside down tree structure. Or it could have been far more free and loose, like in a network structure. And an equivalent analogy of that would be something like the local train systems that connected out of London Waterloo, and how a node's connected to a various number of other nodes, some very complicated system. Now the problem with that was that it very much depended upon what you actually purchased at the time. So it was likely that when you bought some hardware, and you would have bought the software that went with that hardware, then you would have been effectively being locked into that product. Your data would have been bound into the actual software, the data structures that were just being advocated by that particular company, that particular software product. And that was really messy because it wasn't very maintainable. And things remained that way until a sort of landmark paper was published by E.F. Codd. And this is one of those papers in computer science history that basically changes the landscape of computer science and computer sort of science data architectures from that point onwards. And it's called A Relational Model of Data for Large Shared Data Banks in 1970. And what really transformed the way that we think about data structures was this notion that what we should do is, rather than have a kind of free range, different models, different architectures, different approaches to storing data, we should lean very heavily on mathematical models for data. And there's a particular sort of area of mathematics that uses this notation and this notion of this thing that's called a relation, and it leans very heavily on that notion of a relation. Now the advantage of basing your sort of theory, basing the way that you store data on a mathematical structure and a mathematical theory, is that these things are very well defined. People agree on what these things are. So of course, if you've got that baseline, that base architecture, that bedrock, then you know there's going to be consistency between the different way that these bits of software, these different theories will interact. Now in this context, we can regard the relational structures in mathematics to be like set theory. You've done set theory, and often later on you'll see we'll talk a bit about union, intersection, those kinds of things. Here's the definition of relation, and you can see that seems quite complex. Now, this isn't a mathematical course or a sort of computer science course, but so I'm going to make some sort of generalizations just so you get a flavour of what it actually translates into. That's the formal definition of a relation, but you can visualize a relation very simply in a sort of classical form as a table with rows and columns. But you do need to remember that this is one of the key points of the relational model. This is not how the data is actually stored, actually on the hard disk. And this notion that this is an abstraction is one of the key principles behind the relational model. We're not going to focus so much on the sort of binary patterns, the Unicode or the ASCII codes, or the actual formatting that's required to store this information on a hard disk. We're going to take a higher order view. We're going to take that abstract view and think about what's the actual meaning, what's this data actually telling us. Now, there are a few terms, and I'm just going to introduce those as we work our way through and refer back to this example. This is the sort of classic employee table. So this is a table that contains information about people who've actually been employed. It's got employee numbers, names of people, when they were employed, and salaries and things like that. So an attribute is a named column in the relation, and a domain is a set of allowable values. What does that actually translate into? Well, if we go back to the table, what it's saying to us is that each column should have a unique name. And so if you've come from the spreadsheet world, this is more formal than that, because you may well use spreadsheets and you may well sort of try to put the same kind of information in each column. Databases and the notion of a relation in the database is such that if we designate that a column is actually going to contain sort of employee names and has that attribute name of employee names, that means that's the kind of data that we would see in there. Now, saying that more formally, more mathematically if you like, here's the definition. It says each attribute has a value that comes from the allowable domain. So what that actually means is that if I designate a column to be hire date, then we will only ever expect to find hire date in that column. We wouldn't sort of travel halfway along the column and suddenly find it says green or has a tax code or something like that. So that's important for the predictability. When the database is being used, we only expect to find hire dates in that particular column. And in fact, when you actually create a database table, you create a database, what you're actually doing is you're specifying those columns, giving them names, thinking about what that column actually means and what kind of data will actually be stored in there. Is it going to be a number? Is it going to be a date? Is it going to be a character? How wide, how many characters will fit inside that column? Now, every attribute, in other words, every column must have a unique or distinct name. Every table that we have inside our database must also have a distinct name. So databases don't just consist of a table or a relation. They have multiple tables and relations. Now you'll notice that I'm starting to use the terms interchangeably here, table and relation, but there are some differences, but I'll come back to those later on. So let's imagine we're actually storing information about employees. So this is a table, and as you can see, I've given it the name EMP. This is the EMP table, and if we have some other tables, they've got to have unique and distinct names as well. So for example, we could have a department table, and we could have a grade table. And the department table here basically says where the departments are located, what the department name is, and where the location of the department is. And then we have a grade table, and what the grade table does is it tells us the salary range for someone on a particular grade. So if you look at grade 3, for example, people who are appointed to grade 3, their salary would range between 24,000 and 29,999,000. So names must be unique, table names must be unique, but you may find, and I just mentioned this in passing, that sometimes names are duplicated in other tables, names are duplicated in other relations. For example, you may have spotted that we've got department number in the EMP table and we've got department number in the department table. And what we're doing here is we're actually modelling a relationship between those two tables. By having department number in the EMP table, what it enables you to do is to actually sort of follow across. So if you look at Bell, for example, on this slide, if you travel across, you'll see that Bell is actually in department number 3. And then if we look at the table at the bottom, which is the department table, department 3 is sales, and you can see that that's based in Birmingham. So what we're really saying is that there's a relationship between these two tables. We've got an EMP table, an EMP relation, we've got a department table, a department relation, and Bell, who is in department 3, we can travel through into the department table and we can see that that is the sales department in Birmingham. Certain other rules then? Well, each value inside one of these cells is what we would describe as atomic. Now what that actually means is that we wouldn't, in the day-to-day running and the usage of the database, we wouldn't typically split the information to be any lower than the values that you can see inside the cell. So for example, we might say, what job does Bell have, and Bell obviously has sales, it wouldn't make a lot of sense to go, what's the third letter of the jobs that Bell has? We wouldn't typically think of the day-to-day operations of the database, sort of start slicing into smaller parts of the data values. Now you'll notice I use the word typically because sometimes, there are occasions, for example, if you look at hire date, we could go, oh, let's find out which particular year we hired the most people, and that's when we would actually have to dig a little bit deeper and actually extract the year. So that's why I've used the word typically there. Typically, you don't go any smaller than that. You don't split the atom, this sort of atomic value, this notion of atomic values that we have inside the cells. Some other words then, well, a tuple or a tuple is a row of the relation. So we've got some examples here. There's one, and another one, and another one. And obviously a relation or a table is made up with loads of those. Cardinality is the number of tuples in a relation. And you can just basically just count them off like that. And so that we would say that has a cardinality of 14. Now I'm just putting these words into the slide so that you see them if you do any of the background reading. To be fair, I don't talk about degree and cardinality that much. Degree is the number of attributes, so in other words it's the number of columns. And so we would say that this has a degree of 8. Now, because this is based on the notion of a relation, and we know that relations are very close to set theory, there are some important principles that come through. Ordering it doesn't really apply in this model. So I'm using the sort of standard set notation here, which is braces and commas, those kind of curly brackets that I've indicated are in green on this slide. We would say that all of these are equivalent. It doesn't really matter about the order. They are equivalent sets. So what does that actually mean when it comes to information that's inside our table? Well, attribute ordering doesn't actually make any difference. So if I take this table, for example, and you can see we've got employee numbers, names, the jobs they have, who their manager is, when they were hired, and their salary and commission and department number. And what we could do is we could just grab a bunch of those and we could shift those to the other end. And if you think about it, you'll notice that if you travel along one particular row, even though we've ordered the bits of data, each relation, each row is still valid. That data is still the same. It doesn't matter whether we've got hire date first and ename second, or ename first and hire date second. It's still the same. Attribute ordering doesn't actually make any difference here. Similarly then, tuple ordering doesn't make any difference either. Now this can be quite odd sometimes to actually think about this. Inside the relation, inside the table, ordering it isn't important to us. In fact, we can't control the ordering. So over the lifetime of the database, when it's actually in operation, what could happen is a whole bunch of records could just suddenly be sort of placed notionally at the top. And it doesn't really matter to us. Now, I'm not saying that ordering never occurs, because, for example, we could grab that data and we could print it out, we could print it to a screen in a particular order. I'm talking about the way that the data is actually stored inside the relation. And when this is implemented inside a database product, inside the database table itself. Ordering isn't important to us. And in fact, you just don't worry about it. During the day-to-day running of the database, records might be being modified, they might be being added and deleted. So we just go, well, we don't care about the actual ordering inside the table. It's only when we actually create reports, print information to a screen, where we might start ordering information. Inside the table itself, inside the relation, we just simply don't care about the order. One of the other properties that we have inside set theory and relations is that this notion of duplicates doesn't really occur. So you could have multiple instances of an item. These would all be the same set. Now, what does that actually mean when it comes to a relational or database table? Well, every row, every tuple is distinct. Now what that actually means is that every row, every one has to be unique. Now to actually make that occur, we might actually have to introduce a particular column ourselves, a particular attribute ourselves. We'll talk about what that means in practice later on. But if you've ever done any kind of database work, then you're probably thinking about key fields. A key field is a column which has a sort of unique representation, a unique value that enables that to be true. But we'll come back to that at a later point. Now there are some alternative terminologies here, and it very much depends upon whether you're studying this sort of using in academia, or using a piece of software, or using a kind of trade book. So formally and mathematically, you might see we talk about relations, tuples and attributes. Some textbooks might talk about tables, rows and columns, and often those are textbooks which are sort of bound to a particular product, use Oracle or use Access, something like that. Some trade books might talk about file, records and fields, and that notation is still out there, although perhaps it's a little bit old-fashioned nowadays. Typically, in these introductory slides, I typically talk about tables, rows and columns, but occasionally I'll lean back on relations, tuples and attributes. There is a difference going on here because the relational model, and remember that's the mathematical model that all of our database products are actually going to be based on, that's a theory. And what actually happens is that most database products attempt to implement that theory, attempt to use the relational model, but there are a few bits where it doesn't quite work, and we'll come to those when we look at it in practice.